By the I have already shared the first assignment. Okay, and have you seen it?
Yes.
Have you gone through it?
Yes, sir. Yes, sir.
Yes, sir.
Yes,
Okay.
sir.
So maybe the next week we'll complete the first chapter, and the meantime you can start solving the assignment problems. Okay. So
Yes, sir.
the idea here is we are discussing the theory part. As I said, very some typical assignment problems will solve during the lecture. Okay, and the rest of assignment problems you'll work yourself, and for that you'll get some marks. For example, if you submit this assignment successfully with correct answers, then you'll get 2 marks. Okay.
The total assignment marks 2 marks.
2 marks. Okay. And I have already explained the reason behind it, that you'll get 2 marks. In the other hand, some assignment problems will come in your exam. Again, you'll get some mark if you solve successfully. So it is essential to solve each and individual problem mentioned in the assignment. You are free to discuss among yourself to make your doubt or queries clear, and if you have any more specific doubts, we will discuss on that during lecture hour. Okay, let me first share my laptop screen.
This call is now being recorded.
So just now I have shared my laptop screen, and I hope it is visible to all of you. And here is the today's lecture note. Is it visible?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, everybody please go to mute mode. So in the last class we did discuss about harmonic oscillator under the influence of damping force or resistive force. And in today's lecture we will be discussing about harmonic oscillator when we have a resistive force called damping force, also some external force, right? And the oscillator will be called as forced damped harmonic oscillator, in short FD, or sometimes people call forced oscillator, because the harmonic oscillator which is also under damp is in the influence of the external force, which is represent F subscript ext. Okay, so what we have to do? We have to draw a schematic diagram, figure out the force components associated with the oscillator, and then we'll get the force balance equation to get the equation of motion, and there we'll get the solution, that means the displacement of the oscillator, the velocity, acceleration, and therefore the total energy of the oscillator. So that's the roadmap about this forced oscillator. So here is the schematic diagram, and again we'll work with horizontal spring mass oscillator system. You can also work with vertical spring mass oscillator system, even the pendulum case. So we have an external force, you can see Fxt, and the oscillator will now forced to move along the direction of the external force. For example, if the external force is towards right direction, the oscillator is forced to move here. And in order to get oscillation, this external force should not be unidirectional, because if you have in unidirection, what will happen? So then the oscillator will keep continuing to move the right direction until and unless the spring is, broken. So the external force should, the direction should be back and forth, so that the oscillator will, oscillate around the mean position. So we'll see what could be the mathematical expression or the equation that are associated with the external force. So do remember it is time dependent. Okay. And as I am telling you, whenever you have a schematic diagram, whatever symbol or notation you are using for that schematic diagram, you have to explicitly mention them. Otherwise, they don't make any sense. So K, M, X naught, F subscript S, A vector, which is also time dependent, FD, all those things they have mentioned here. Okay. So although I have not mentioned, for example, I did not mention what is, FD. I did not mention what is FS. So you have to mention them. Okay. So again, let at given instant of time, xt is the position of the oscillator and at is corresponding accelerations. So now, so the oscillator will force to move towards the external force direction, and whatever the acceleration will achieve by the oscillator, that will be due to this external force, and this external force will compensate with the spring force as well as damping force. In other words, the external force, spring force and damp force, right, will add them, and then will net force, and the oscillator will move with an acceleration a. Due to this, the net force, net force acts on the oscillator at that given instant of time t. Is it clear? So we have external force, then the spring force and damping force, which is opposing force, will get the net force, and the oscillator will force to move by this net force with an acceleration a. So here we have an equation. So what is the net force? Will be sum of these three forces: spring force, damping force, and external force. And the oscillator will move with an acceleration net force, Fm, which is F of m. Okay, so now if you balance it, then we have this equation. We know the spring force minus kxt, damping force minus bpt plus F of xt. So do remember this negative sign indicates they are opposite in nature compared than the external force. Okay, the accelerator will move with this acceleration a. So now, as I said, we know the spring force, damping force mathematical expression, but until and unless we don't know that external force, we cannot progress. So therefore, it is essential to know the exact mathematical form of this external force. And then, as I said, in order to continue oscillate, so the external force should act back and forth. And what could be the simplest form? So here I have written down a simplest form, which is F naught cosine omega naught t. So do you remember the cosine is an oscillatory function? So therefore, the external force will act back and forth with some period, which is omega, capital T, you can say, or the 2 pi over omega. For the oscillator will move with that frequency. Okay, so you can also make argument that can I choose other form of this external force? Yes, you are free to choose in a condition that it should be periodic in nature, or it should give the indication of that the oscillator is moving left and right. It should not be unidirectional. For example, some linear function ax. Okay, so it's unidirectional. So therefore so we cannot choose such form external force. And here what is F naught? F naught is the maximum amplitude that associated with the external force. So if I draw a schematic diagram of the external force, what you will get? You will get something like this. Okay, so this will be maximum and F naught, and this is the frequency, which is 2 pi over omega, or time period. Okay, which is your time period. So now if you make further simplification of this equation, you will get the expression 1. Okay. So now we have already, come across this form gamma, which is the damping coefficient, omega naught is the natural frequency of the oscillator. So now we have in the right hand side. So this is also a differential equation, and some of you might have already come across such a differential equation, but do remember that it's in fact a second order ordinary differential equation, and in addition to that, it is also linear and non-homogeneous. I hope some of you or all of you know linear, homogeneous, or non-homogeneous. Okay, so linear means the derivatives, okay, should be free from the higher order terms. For example, you should not have like the square of that, like dxt over dt square or cube. Okay, so the power, sorry, you can say the equation is free from the higher order power. Okay, so therefore it's called linear. So whatever the differential equation we have shown for simple harmonic oscillator or damped harmonic oscillator, they are linear, but they are homogeneous. Because if the right hand side, so do remember the right hand side term, so there is no this independent term, x of t is not here, so this is some other term. So let me write down. You can also ask your math teacher, those who do not know, if you have a differential equation, normally we can have, let me write a power term, right? So let me write in differential form. Let's say in, let's say, x over dt, right? dn minus 1 x over dt, and you can say that then xt. Okay, so if this is not equal to 0, then it's called non-homogeneous, and if it's a 0, then it's called homogeneous equation. Okay, so for example, in damped harmonic oscillator case, we have d square x of t dt square plus 2 gamma dx over dt plus omega naught square x of t equal to 0. So you can see the right hand side is 0, so therefore it is an example of homogeneous equation. Okay, and then let me use some power. Let me use the different color. By the way, you can hear me, right? Am I audible?
Yes, sir.
Yes.
Yes, sir. Yes, sir.
Let's say P. Let me write this is Q1. So, and if I say if P Q dot dot dot, let's say if this is 1, that means the power is 1, then this implies linear. And if it's it's not 1, then it's a non-linear. Just in a brief, in a brief statement about linear, non-linear, homogeneous, non-homogeneous. I hope some of you might know all those things, okay, in the 10+2 class. Is it clear so far?
Yes, sir.
Yes, sir.
So now, in short, we have second order, linear, non-homogeneous, sometimes people call inhomogeneous, ordinary equation. So then how to solve it? There are many procedures, but there is a standard procedure to solve this a linear non-homogeneous equation. Okay, So what is that standard procedure that I have written down here? So the general solution of any linear non-homogeneous equation should have two parts, as I have written down here. One is x subscript ct, another is x subscript pt. So the question is here is what is x subscript ct, what is x subscript pt? So x subscript ct is the complementary solution. So therefore the subscript c is appear. C stands for complementary solution. What is that? That we'll see. So this is a complementary solution which is nothing but the solution of the homogeneous part of the ordinary differential equation 1. So when you talk about the homogeneous part of this non-homogeneous equation, which is represent equation 1, what does it mean? That means we'll make the right hand side 0. So that means the solution of the equation 3. Whatever the solution of the equation 3, complementary solution associated with the linear non-homogeneous equation. And this is nothing but the equation for the damped harmonic oscillator. And we have already known the solution for the damped harmonic oscillator. Is this clear?
Yes, sir.
Okay. We have already known. So no need to solve further. Depending on the situation, whether the underdamped, overdamped, critical damped, we have three different solutions. As I have already said in the previous lecture, out of these three solutions or situation, only underdamped is interesting. Why? Because the overdamped or critical damped, they do not show any oscillation, but underdamped shows oscillation. So we'll consider the underdamped solution and we'll throw out the other two cases, overdamped and critical damped. Okay, so now we know that the complementary solution. What is x subscript pt? So let's see. So do remember, this is the standard procedure to solve any non-homogeneous equation. We have complementary solution and particular solution. And the x subscript p represents the particular solution, or sometimes people call integral solution of non-homogeneous equation 1. And how will get that one? xpt. So one should use called complex algebra methods. Some complex, number techniques, algebra techniques, one will use in order to get the particular solution. So what is that? Let's see. Again, I am, repeating. So this is the standard procedure. The detail you can ask your math teacher. Okay. So what is this complex algebra technique will give you the particular solution? So it says that we shall look for a solution of the form of x20 a e to the power omega t. So if you remember, either the force damped oscillator or simple harmonic oscillator, what is the solution for x of t? The initial case solution a e to the power alpha t. We use this initial case solution and then we got the solutions here. But the complex algebra method says, let's as consider the initial case solution, which is x1t, rather than a e to the power alpha t, we have a e to the power I omega t. And this is the initial case solution of which equation? This d square x1t dt square plus 2 gamma dx1t dt plus omega 1 naught square x1t plus this one, the right hand side. So if you look carefully, the equation 4 and equation 1, right? We have f naught m cosine and the variable is x of t, but here the variable is x1t and the right hand side, instead of cosine, we have exponential function e to the power I omega t. Then you might make argue, do I believe it or how do I believe it? So the question, then the simplest way is you substitute, or let's take the, what is the, if you expand a e to the power I omega t, what we'll get? We'll get a cosine omega t plus I a sine omega t. Okay, e to the power I omega t. And now, then the equation 1, right? If we separate these two equations, what we'll get here, we'll get the f naught over m cosine omega t plus I f naught over m sine omega t, the real part as well as the imaginary part. Okay, and then it should multiply with the p factor a. So that, and then if as I said, if we take the real part only cosine omega t, the right hand side will get the cosine omega t, which exactly matches with the equation 1. And right hand side we have again instead of x1t, which will be a to the power alpha t. And in short, what I would like to convince you that intuitively one can think this x1t a to the power I omega t is actually a valid initial guess solution as I split into imaginary and real part. Okay. So that's exactly I have done here. So then what we'll do, once we solve this equation by substituting initial guess solution a e to the power I omega t, then we shall look part of x1t. As I said, because this will give the right hand side exactly this equation 1 right hand side, if not omega cosine omega t. So we'll solve x1t by substituting here, and then we'll take the real part in order to get the solution of the particular integral. Is this clear to everybody? Yeah.
Yes, sir.
Okay. So now, so let's do that. So when you substitute this one in this equation, if you simplify it, you will end with this equation. And then a e to the power I omega naught t, this is nothing but will be f naught over m e to the power I omega t divided by p of I omega. So only mathematics, right? So what is so I omega is the another function which is nothing but the term sitting in the square bracket. Okay, so now we have to simplify it. So as I said, if you take the real part of the right hand side, we'll get the cosine function. So similarly, if somehow we can translate this one in some level of the exponential function e to the power I, then our job will be solved, because we'll have cosine term and sine term. We'll only take the real part, that means the cosine term of this left hand side. So let's do that. So I will do that. So now, as you know, more or less about complex number z, which is x plus iy. X is the real part, y is the imaginary part. Okay, so similarly, you can say a complex let's say f of z, the complex number, which is we can have a, let's say what I can write, let's say if f1 we z plus I f2 z, or more if we expand it by fxy be f1 xy plus I f2 xy. So here this is the real function, this is the imaginary function. Okay, so now so that same procedure we'll do. So if we simplify it, we'll get p of I omega, which is omega naught square minus omega square plus I2 gamma omega. And then this is Cartesian coordinate that I have represented this number here. We have real axis, we have imaginary axis. So omega naught square minus omega square is the along real axis, 2 gamma omega along imaginary axis. Okay, and then everybody knows to translate a function from Cartesian coordinate to polar coordinate. That means xy to r theta or r phi. Okay, and what will be? As you know, the R value will be, let me write down, R equal to square root of x square plus y square, and phi is tan inverse y over x. Yes or no? So we translate Cartesian to polar coordinate, right? So if you do that, what will be R? X square omega naught square minus omega square whole square. What is y? 2 gamma omega whole square, 4 gamma square omega. What is phi? Tan inverse y over x. So that's exactly I have done. So now in polar coordinate, what we'll write a function, let's say f x y, we can write a function to r e to the power I phi. So that I have done here. R e to the, what is r? Phi, that they are mentioned here. So simply complex little bit about complex algebra, and then to translate Cartesian coordinate to polar coordinate systems. And as I said, that somehow we need to translate some exponential function, and that we have got. And by taking the real part, which will be cosine phi, our job will be done. So substituting the pi omega value here, and what we'll get? This equation. F naught over m e to the power I omega t r e to the power I phi. What is phi? Tan in omega under. And taking the real part of x1t, and what we can write? We can, this is the real, the term sitting in the square bracket is real, f naught of omega real, and we can have e to the power I omega naught t minus e to the power I phi. Okay, so that will be your e to the power I omega naught t minus phi. And if you translate, this will be your cosine omega t minus phi plus sine omega naught t minus phi. So now the real part of this exponential function will be simply cosine omega naught t over phi. So that I have written down here. So the and cosine omega naught t minus phi. So now, as I have argued previously, the underdamped, part of motion is interesting, or oscillation is interesting. So therefore, the complementary solution will be your underdamped part of the solution, a e to the power minus gamma t cosine omega naught t plus theta, and the particular integral solution, which is given here. So now this is the general solution that is associated with the harmonic oscillator. So is this clear to everybody?
Yes, sir.
Yes, sir.
And as I said, now even if previously why we did not consider the overdamped or critical damp, because this solution decay exponentially and therefore they do not show any oscillation. And A is the amplitude, gamma as we know, the damping coefficient, omega 1, which is omega naught square minus gamma square. That means the frequency of the oscillator associated damped harmonic oscillator pathway. That means if the oscillator is free from the external force, this will be the oscillation frequency of the oscillator. And if what is F naught is the amplitude of the external applied force. And what is omega? What is omega? Omega is the angular frequency associated with the external force. And then the question is, what is phi? The phi, which mathematical expression is given here, but what is the physical significances of phi here? Okay, so we know theta is in. What is the physical significance of phi? Which is tan inverse 2 gamma omega over omega naught square minus omega square. So what is the physical significance of omega naught? Phi. Okay, so and then what is the next step? The next step is to find the physical significance of phi. And the other, term or other constant or variable, we know the physical meaning. For example, gamma, the damping coefficient, which is B over 2. Theta, the initial phase of the oscillator. Omega naught, the natural frequency of the oscillator. F naught, the amplitude of the external applied force. Omega, the angular frequency associated with the external force. But phi, we know the mathematical expression, but we do not know the physical significance. Okay. So any specific questions so far? Yes or no?
So, what is example for damped force damped oscillation? One example.
Mm, I'll come to the point, right? I'll come to the so this keep in your mind, and I'll come, right? So that we are going to discuss next, okay? But the solution, how did we get the solution? I hope everybody understood, okay? So next, so let's as I said uh, let's try to know what is the physical significance of phi. And as one of you pointed out the examples of the forced oscillator, and what is the consequences, what will happen if you have a forced oscillator. So let me open the next lecture. Just a moment. Okay. So know the physical significances of phi, right? And therefore the energy is associated with the oscillator, and we'll give some typical examples where one can see the forced oscillation can occur. Okay. So before we do that, let's see, can we further simplify this equation 1? Yes, we can do it. So you might ask question, what will happen if we wait sufficient long time? When you say sufficient long time, time is, let's say, very large. Let's say t equal to infinite in mathematical language. When t goes to infinite, what will happen? So this part of the solution, e to the power minus gamma t, what will be e to the power minus infinity is what? 0. So e to the power minus infinity will be 0. So it means the complementary solution will decay. That's exactly same, right? So in a damped harmonic oscillator case, the oscillator will finally settle down at the resting position if you wait sufficient long time. So the complementary solution will 0. So, and since this solution, it lasts for a particular time, right? Depending on the damping coefficient or damping constant of the medium where the oscillator is oscillating, and hence, therefore, it's known as the transient solution. Transient means it will, last for a particular time. Then it will decay or disappears. So the complementary solution is also known as the transient solution. And then since we wait, a sufficient long time, that means the system will get to a, equilibrium state, or other language called steady state. That means there is nothing more to evolve, right? So therefore it's called steady state solution. So the equation 1, that means the solution can be approximated to only particular solution, which is a cosine omega t minus phi. And as I said, so this solution will remain forever and it won't decay over time. Therefore, it's a steady state solution or equilibrium solution. And what is A? A is F naught over this is 1 here. So now here, looking at equation 3, one can find the physical significance of the phi. What is the physical significance of phi? Anybody can tell? Omega naught, What is omega? Omega is the frequency
External force.
associated with external force. A is the amplitude simply, right? So we have many factors that are associated. But what is phi? What is the physical significances? So one can see that the oscillator, what is x of t? X of t is the displacement of the oscillator at a given instant of time t. So the oscillator will oscillate with the same frequency of the external force omega, but there will be some phase lag. I will phase lag. That means the oscillator won't oscillate immediately as we apply external force. The oscillator will oscillate the same frequency of the external force, but there will be time lag. So phi normally represent the phase factor, as that means the time lag between the, so it means the delay between the action of the external force and the response of the oscillator. And if you plot it, let's try to plot it. So the phi phase, right, with respect to the frequencies omega. So now you can have two omega, external applied force frequency, phi is the phase. So let's see what will happen. So now, when the external force frequency is omega naught, right? When the external frequency is omega naught, right? And when phase pi by 2, what will happen? Cosine omega t minus pi by 2 equal to what? Again cosine omega t. So some sine functions, right? So therefore it will be 0. So that's exactly here. So here, this is the mean position. And similarly, so let's consider two extreme situations. One is low damping or high damping. So let's say low damping, when we have, let's say, zero phase. When we have a zero phase, then a cosine omega t. Okay, so that means there will be no delay. So the oscillator will oscillate frequency of this. And when phi equal to pi, that's again the same. But when we pi by 2, it will be out of phase. And depending on the damping, whether it's low and high damping, we'll have the response curve will be here. Because if the damping will be high, then the response, the delay will be more. If the damping is low, the delay will be less. So that's the plot represents. So in short, what we understood, the phi represents the phase factor that explains the delay between the action of external force and the response of the oscillator. And if the damping medium is low, the response will be fast. That means the delay will be less. That as you apply the external force, the oscillator will oscillate with the same frequency and synchronized manner with the external force. If the damping is high, it won't be synchronized. Got it? Okay. And then you might ask question, what will happen omega approaches to omega naught or omega equal to omega naught? That I have represent this curve. And that situation is the resonance.
Hello, sir.
Yes.
So what will happen means at resonance in post-damped oscillation, at resonance what will happen?
So that I am going to talk about. Okay. So you understand, right? So we have this response curve and we are trying to look at
Okay, sir.
what will happen the external frequencies approaches to the natural frequency. Okay, so here I'll give you any classic examples. You might have heard or you might have seen some movies. When a group of people, let's say soldier, they cross a bridge. Soldiers, they normally do that, right, or marching, synchronous manner, right? And when they kick the floor or the road, they exert force or apply force in a synchrony manner, some external force, some periodic, left, right, okay, periodic manner. Okay, so you can think this is external force. And when they cross over a bridge, then the commander of the soldier will instruct them, don't do marching over bridge. The question is why? Because the bridge, right, it is some kind of oscillator systems, and it has natural frequencies. The natural frequency depend on the mass and the spring, so spring constant here, the flexibility of the bridge, right? So the spring, anyways, even if any structure, the building, bridge, or whatever structure we can see, it has some natural frequencies, which is omega naught. Okay, and when soldier will cross over the bridge, what will happen if they do marching? If unluckily the marching frequencies, because they'll do left and right, matches the natural frequency of the oscillator, then the resonance will occur, and when the resonance will occur, the oscillator bridge will start oscillate the maximum amplitude. It means the maximum, that means the allow oscillation amplitude of the bridge exceeds, and hence the bridge will collapse. So therefore the commander in charge instructs soldier never ever do marching over the bridge, to avoid that the marching frequency should not match with the natural frequency, otherwise the bridge will get collapse. And another example during earthquake. So nowadays there are some which earthquake resistive, but those buildings which are not earthquake resistant, what will happen during the earthquake? The earthquake will transmit with the certain frequencies. If somehow it matches some particular or certain buildings, then the building will oscillate back and forth maximum amplitude, and they will get collapse. And you might have heard about the highest skyscraper in the world. So that is Burj Khalifa, right? And even if you can look at before that, the Taipei 11 or 103, okay, so 103 floor based skyscraper was the highest tallest skyscraper before Burj Khalifa. So therefore, if you go through this Taipei 103 building, what we'll find at the top, so there is a called tuned damped oscillator. It's in a ball kind of shape, and they are balanced by piston. What will happen when the building, a type of building, will start oscillating? It will oscillate some amplitude, right? And that force will suddenly transfer to the damped oscillator. It will absorb, because the damped oscillator attenuate, or the unit will try to reduce the oscillation. In that case, one can avoid the collapsing of the skyscraper due to the earthquake. And similarly, so you might have heard about the Statue of Unity, right? Yes or no?
Yes, sir.
Yes, sir.
So if you go to the documentary, you'll find the statue, just beneath of the shoulder part of the statue, two tuned damped oscillator are installed, because when the statue will start oscillating the maximum frequency, the energy will transport to this tuned damped oscillator. And what is the duty of the damped oscillator? It will try to decay of the oscillation, right? The energy or the force absorbed or given by the earthquake to the building, it will transport to the damped oscillator. So therefore, the building or the statue won't oscillate across their threshold limit. Okay. So by the way, so everybody wants to avoid resonance. As I gave the example of Taipei 103 building, Statue of Unity, even any skyscraper. So they install tuned damped oscillator in addition to other earthquake supporting mechanisms, or you can say. So So as I said, if the resonance happen, then the oscillator will start oscillating maximum frequency, and then it will have some catastrophe. So that is resonance occur when the external applied force frequency approaches to natural frequency, and during resonance the oscillator start to oscillate maximum amplitude. Okay, so we have this solution, and as per the definition, the amplitude will be maximum. This amplitude, you see, the cosine omega naught minus pi, the maximum is 1, minimum is -1. But whether the x of t will be maximum or minimum, that depends on this factor, the factor sitting beneath this one. So in order to maximize the amplitude A, so this should be minimum. So this minimum means the first derivative should be 0, and in addition to that, the second derivative must be 0. So you might have been knowing, right? So a function is minimum when the first derivative is 0, and you equate whatever the solution will get while equating the first derivative in the second derivative. If the second derivative is less than 0, it means maximum. When the second derivative is greater than 0, it means minimum. Yes or no? Have you ever tried to find minimum and maximum of a function at a given point? So this is the standard procedure. Do the first derivative, get the solution, do the second derivative, and put that the solution. If it's less than 0, maximum. If it's greater than 0, then minimum. So that's exactly in order to get the maximum value. And here I am not solving in detail. If you solve it, you will end with this, omega equal to this function. And since we maximize this function, so therefore the frequency that we obtain is known as the resonant frequency of the force oscillator. So we got that the resonant frequency is omega naught square minus 2 gamma square square. Okay. So don't get confused with damped frequency. The damped frequency, which is omega 1, is omega naught square minus gamma square. But here omega naught square minus 2 gamma square. And if you substitute this below in equation 3a, because we will try to get the maximum amplitude. What we'll get? We'll get the maximum amplitude, because this we obtain by maximizing the function. So therefore, if you substitute, then we'll get the maximum. This. And now we replaced omega by omega r, the resonance frequency. And since the amplitude is maximum, we donated the resonance frequency. So the resonance frequencies, if we further simplify it, so we'll end with this. So only mathematics, nothing great, right? I might have skipped some step, but you can do the detailed solution. So what we got to know that the resonance frequency by this expression, above expression, and the resonance amplitude by here. And you can see the resonance amplitude, right, is directly proportional to the external force amplitude, the inversely proportional to damping constant, also inversely proportional to the square root of omega naught square minus gamma square. Okay, so what physical things, or what does this actually represent? What is the physical significances? So in order to get the physical significances, we should look at weak damping or strong damping. So for weak damping medium, gamma is much less than omega naught, because V is very less. Okay, so gamma is much less than omega naught. So therefore, the gamma square term under the square bracket can be neglected in comparison with omega naught square. So omega naught square minus gamma square can be approximate to omega naught square. And we further simplified it. What will happen? The amplitude AR will be F naught over B square root of omega naught, which is F naught over B omega naught. And what is the resonance amplitude? We'll neglect gamma square here. Here we have omega naught. So the resonance frequency is omega naught, and the resonance amplitude F naught of B omega naught. So note here, if the resonance will occur in low damping medium, the resonance frequency is nothing but the natural frequency of the oscillator. The resonance amplitude is directly proportional to external force amplitude and inversely proportional to damping constant. So this means if the damping will be less, then the resonance amplitude will be more. If the damping is high, then the resonance amplitude will be less. So that's the physical things we can extract from this equation 5. Okay, so this is all about forced damped harmonic oscillator and its consequences. That means the resonance. So everybody should try to
Hello, sir.
avoid resonance. Yes.
So, the unit of omega and gamma are same. Means frequency and damping constants units are same.
Yes. They must be same. You omega naught and gamma. Gamma is what is gamma? B over 2.
Damping constant.
Okay.
Damping
And
constant.
what is B? If you remember, force damping force is minus BV, and you can get the dimension of B, and you know the dimension of beam, and you can equate. Okay.
Yes, sir. Good.
Okay. So this is all about force damped harmonic oscillator, and as I said, its consequences in the form of resonance. So any questions or doubt? By the both lecture notes as well as the recorded video I will share, like I have already shared last lecture, as well as the recorded video. Those who have doubt, they can go through the lecture note as well as the video lectures. And I think your doubt will be cleared. So any specific question? Okay. So now the next class we'll talk about what will happen. So do remember here we discuss by considering only single oscillator. So in the next class we'll talk about what will happen if we have more than one oscillator. That we will discuss, okay, in great detail and try to get the solution. Okay, if there is no question, I think we should stop here, and you please solve your assignments, right? And by next class we'll finish the oscillation chapter, and after that we'll talk about the next chapter, namely optics. There we'll begin with waves, and then the light waves, then diffraction, interference, polarization, and so on. Okay.
So attendance.
Attendance will be recorded automatically. Don't worry. Okay.
Okay, sir.
Okay. So no question. Bye. We'll meet next class. Okay. Bye.
Okay, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Thank you, sir.